In the previous lectures, we have studied some basic concept of differential calculus for multivariable functions. Today, we will study the central theorem of differential calculus, the inverse function theorem. Firstly, I will state the theorem here. Suppose omega is an open subset of Rn, and f is a map from omega to Rn, which is continuously differentiable. C1. And A is a point in omega. The condition is the Jacobian determinant of f at this point A is not zero. So what this means, we know that the derivative of f at this point A can be considered as a linear map from Rn to Rn. This is linear. Now, the determinant is not zero means that this linear map is invertible. So, our condition for the inverse function theorem is just that the linearization of f at this point A is invertible. Naturally, we will expect that f is invertible in some sense. But as we know, the differentiability of f at this point A and its derivative depend only on the local behavior of f near this point A. So we could not expect f to be globally invertible. It can only be locally invertible at the best. What locally invertible means? This is the conclusion of our theorem, the inverse function theorem. The exact meaning is that there exists open subset of Rn denoted by U and V such that A belongs to U and B is the image of A under our map F belongs to V. And F as a map from U to V is invertible. It's injective and surjective, so it's invertible. So it has an inverse map. The inverse map is a map from V to U. It's also smooth. So this is the inverse function theorem. Of course, this U is a subset of omega. Okay, this is our main theorem for this lecture. To prove this theorem, we need the following proposition. If the Jacobian determinant of f at this point A is not zero, what can we get? There exists epsilon positive, kappa positive, such that for any xy near this point A, more precisely, xy belongs to the ball centering at A and its radius epsilon. We have this is the distance of the image of x and y under our map F. This distance is no less than kappa multiply the distance between x and y. Let us look at this consequence. Obviously, this means that f is injective on this small ball because for x and y, for different x and y in this ball, fx could not equal fy. So f is injective on this map. Our theorem want to show that f is immutable. Firstly, as a consequence of this lemma, f is injective. Okay. So we prove this lemma. To prove this lemma, for simplicity, we denote the derivative of faa by a. This is just for the simplicity. Denote this metric by a. And we consider a map. This map is phi from omega to Rm, defined by phi x is x minus a inverse fx. We consider this map. So this map is of course C1, because this is the identity map, very smooth, and f is C1. This is a linear map. The composition is also C1, so phi is C1. And the derivative of phi at our point A, what's this? This derivative, here, this is the identity map. The derivative of this map is the identity metric, the n by n identity metric. And the derivative of this composition, this is a linear map. The derivative is itself. And the derivative of f at a is f prime a. So by the chain rule, we know that the derivative of this part is just the multiplication of these two metrics. But f prime a is exactly a. So this is also the identity metric. Therefore, this is the n by n zero metric. Hence, the metric norm of phi of the derivative of phi at a is 0. Do you remember what the metric norm means? The metric norm of a metric is the maximal value of this function over the unit sphere. So this is the metric norm. If this is a 0 metric, of course the norm is also 0. Okay. Now, by this map, this function is obviously continuous. Okay? You see? Phi is C1, therefore phi prime is continuous. And taking metric norm is also continuous. So this is the composition of two continuous functions. It's continuous. And the value of this function at this point A is 0. So we can choose an epsilon small enough such that for any x near A in this ball, center at A and a radius epsilon, we have the norm of the derivative of phi at this x close to A, less than a half. This is by the continuity of this function. Now what should we do now? We have a point A here, and we have a radius epsilon. We want to solve any 2 points in this ball. We have this inequality, so we choose any 2 points x and y here, x and y in this ball. For x, y in this ball, we can apply the mean value inequality to our map phi. and we can get some point between x and y. Between the segment x and y, there is a xi here, such that the distance between phi x and phi y is less than or equal to the metric norm of the derivative of phi at this middle point, intermiddle point, times the distance between x and y. But as x and y in this ball, any point between the segment, in particular our epsilon, our xi here, xi is also in this ball. So this will not greater than a half times x, the distance between x and y. Okay. On the other hand, the left-hand side of this inequality, we have however, phi x minus phi y, what's this? By the definition of phi, this is exactly x minus, this is phi x minus phi y. We rewrite this in another form. This is exactly x minus y minus A inverse fx minus fy. So we can apply the triangle inequality to get the norm of this first part minus the norm of the second part. And by the definition of metric norm we record here, we have what we have. We have A inverse fx minus fy. The norm of this vector will not greater than the norm of the inverse metric. This is by the metric norm, by the definition of metric norm. We have this inequality. Apply this inequality here, we can get this. This part we apply the inequality there. So this is fx minus fy. Putting these two things together, what we get? A half of this distance is not less than this distance minus this. So combine these two. This is 1, this is 2. From 1 and 2, we get what? This is equal. Therefore, we move this to the right hand side and then move this to the left hand. We move this to the left hand side and move this half to the right hand side. We will have this inequality for any x and y in this ball. That is our deserved result. So this number we denoted by kappa, and the lemma is proved.